So class, this is chapter 3. In this chapter, we will learn how to design the combinational circuit. So actually before this, in the previous chapter, you have been introduced to designing the combinational circuit already. But in this chapter, we will look into in detail some of the very important circuit in digital electronic or digital hardware, and how to design that kind of circuit. So in this chapter, we will look at the first one is the multiplexer, right? Has been introduced to you before, but we will look in details the variation of multiplexer and how we write the code to describe the multiplexer. And we will look at decoder and encoder, a very important circuit in digital hardware as well. Multiplexer is normally used in bus design in computer and in digital hardware, right? For example, we have many wires, and at one time, only one wire must be selected for enter the module or enter the register or whatever. So we need a multiplexer to isolate that output data with the data that we don't want, right? That is the use of multiplexer. And we also need to learn decoder and encoder, right? Decoder is normally used in digital hardware for uh, decode the address in the memory, especially, or decode uh, the information, all right? Change the one kind of information to another kind of information. Same like encoder, means that we normally use encoder to reduce the size of the data, right? Make it more compact. Normally we can use the encoder, right? And come to the another important circuit in digital hardware, which is the adder, used to add number and do the arithmetic operation, very important in computer. And also the subtractor, and how we do the subtract in digital hardware. And this is very related to how we represent sign number in hardware. And we will see also what is comparator, how to compare a number. And this is very important also in digital hardware in computer, right? And next, we will look at multiplier, how to design a multiplier, how to multiply a data, a number. And last one, we will look at arithmetic logic unit, or ALU, in the computer, right? So it's the most important, is the brain of your computer, the arithmetic and the logic unit, in your handphone, in your calculator, in your computer, right? The circuit that need computation, all need the ALU, right? So again, combinational circuit is the circuit which output on value depend on the present combinational input values, just like what I explained before. The combinational circuit is the circuit where the output of the circuit is changed, immediately, all right, when the input or one of the input change. For example, we have ABC input, we have F output. When one of the input ABC is changed, it will immediately affect the output F. That will be a combinational circuit. We have another kind of circuit, is called a sequential circuit, where we will learn in chapter 4, where this circuit, the output not only depend on the input, but also depend on the past value of input or output, right? That is called a sequential circuit, or in other words, this is a circuit that has a memory. Uh, and we will see later that both combinational circuit and sequential circuit are actually a basic block to develop a complex digital circuit. So most complex digital circuit that we have today is the combination of these two kind of circuit, combinational and the sequential circuit. So in your computer, in your handphone, in your calculator, both the type of circuit is used together, right? These block are logic gates. This means the combination circuit, is a logic gate, multiplexer, decoder. Basic register is the sequential circuit, and controller also the sequential circuit, right? So now let's look at the first combinational circuit that we have, the very useful one and very common one, right? Which is the multiplexer. So the multiplexer is the circuit used to select the input and output and send the input to the output, or only one input to the output at a time, right? So for example, for the 2-to-1 multiplexer, where we have two inputs and one control signal and only have only one output, and at one time only one input is allowed to go to the output. So in this case, if s equal to 0, f will equal to W0, and if s equal to 1, the output f is equal to W1, exactly like this table. And the complete truth table is this. This is simplified truth table. The complete truth table is this, where we will see that if s equal to 0, so we will see f will follow exactly W0, 0, 1, 0, 1, 0, 1, 0, 1. But if s equal to 1, f will follow exactly what is at W1. This is 0, 0, 1, 1, 0, 0, 1, 1. So that is a 2-to-1 multiplexer. And the circuit is this, because we have the truth table here, so we can generate the logic equation. From logic equation, of course, we can generate the logic gate or logic circuit. This, and we can write the Verilog code to describe this circuit, whether we use uh, data flow modeling, we use straight away write the logic equation and using a sine keyword, or we can also use the behavioral code like this, always block, where we have in the sensitivity list, we have W0, S, and W1. And if S equal to 1, right, F equal to W1, else F equal to W0, exactly based on this, right? So if we have this, actually we can create the Verilog code already using behavioral modeling. Very easy. And we also have more bigger multiplexer, which is the 4-to-1 multiplexer. And of course, if you have 4-to-1 multiplexer, you need to have 2-bit control signal, right? Because to represent all the possibilities here, you need to have 2, right? From 0, 0, 0, 1, 1, 0, 1, 1. So these are all the possibilities that you need to have. And this is the truth table, the simplified truth table. And of course, if we have truth table like this, we actually can create the Verilog code based on this truth table. And straight away, we can use the case statement, right? Just same as just we have learned. So in this case, we use case S, and S is 2-bit and 0, 1. And if 0, 0, if 0, 0, F should be W0. If 0, 1, right, 0, 1, F should be W1. And if 1, 1, we have W3 here, and case done. So we can have this 4-to-1 multiplexer very easily. Or if we want to use data flow modeling, where we need to have the Boolean equation. So we need to derive the Boolean equation for F. But it is not easy, right? We need to have all of this. Or you can use the structural modeling, where you can instantiate the gate. All right, so you have the flexibility for writing the code. Right, in this case, the easiest way is to use the behavioral modeling, because we have this truth table. We can straight away write the code. And we also can use the hierarchical design, right, by using 3-2-1 multiplexer connected like this. And we can have the 4-1 multiplexer as well, right? And we can instantiate the module, all right, mux 2-1. So here, mux 2-1, we can use it 3 times and do the connection like this. So W0 is connected to this, W1, and so on and so forth. We can have the same one. So again, this is very flexible in Verilog. Yeah? If you have this design, you can use this, right? So that will be the multiplexer. And of course, you can have a bigger multiplexer, 8-1, yeah, 16-1, or more than that. Should be no problem, right? And you can write the Verilog code for this very easily. So again, if you have a big circuit, for example, 8-1, 16-1, 32-1, the circuit is quite big already, and to uh, to use data flow modeling is quite impossible now. So the best way is to use the behavioral modeling, right? Use case statement is the easiest way. Now go to the next one, which is the decoder, right? So the binary decoder is the combination of logic circuit that convert a binary value to a set of signal. Normally we use in memory addressing and decoding, very important in computer hardware or any digital hardware, right? Because we have memory that has many addresses. Yeah. So for example, if you have 1 MB memory, so you need to have 1 MB addresses, right? Which is very, very big. So we will use what we call the memory address decoder to decode the address, so that we can go to the correct location or correct address in the memory. And this is an example of binary decoder. So we have one we call the enable input, and we have an input, means that many inputs, and we have 2 power of n output. So if, for example, input is 3, so the output will be 2 power of 3, which is 8. Yeah. If your input is 4, so you have 2 power of 4, which is 16, and so on, right? And when we look at the symbol, graphical symbol, we can have something like this. This is the simple 2 to 4, right? 2 input, 4 output. Yeah, and this is a truth table. So the for this decoder, output here will be activated based on this value, and this decoder also depend on one signal. We call it enable en here. If en equal to 0, so the output will not depend on the W1 and W2 anymore. So means that this is don't care. The output here will be always 0 when enable equal to 0. But when enable equal to 1, so the output here will depend on this W1 and W0. So in this case, if 0, 0, Y0 will be 1, others output will be 0. If 0, 1, Y1 will be 1, others will be 0. And 1, 0, Y2 will be 1, others 0. 1, 1, Y3 will be 1, others will be 0. So this is the behavior of this decoder. And when we derive the circuit from this, yeah, of course we can derive using a Boolean equation, right? Or very easy, y1 equal to en equal to 1, en 0 0 means that this is 1 0 0, or W naught, W0 naught, W1 naught, and we get Y0 and so on. So this is the logic circuit. And from this, we actually can describe the Verilog code, derived or describe the circuit using Verilog code. And the best way is to use behavioral modeling, because we have the truth table already here, and this is one way, this is another way. So the first way is to have something like this. If enable equal to 0, so the output Y will be equal to 0. And else means that if enable equal to 1, the output Y will depend on this W0 and W1. So we can use case W. If 0 0 0 0, so the output Y will be 1 0 0 0 1 0 0 0, and Y we declared here as a 4-bit number, which is start from Y0 to Y3, Y0 to Y3 here, right? And with 0 1, so 1 0 1 0 0 until we have this, and case done, right? Or we can write something like this using concatenate, like this, right, where we combine En and W together, En W together, and we have 1 0 0 1 0 0, the output will be 1 0 0. If 1 0 1 1 0 1, En and W, 1 0 1, we have Y equal to this. And other than this means that you can use the default keyword. Default keyword. Default means that other than the one that we described here, all right? In this case is this 0 0 0 0 0 0 or 0 0 1 and others, right? Other than this, so we can use default. So other than this, Y should be equal to 0 0 0 0, and this will generate the same circuit, right, for us. And we can create the 3 to 8 decoder using the 2 to 4 decoder, and connection is like this, right, where we can have the truth table like this. This is 3 to 8, 3 to 8, right, see? And from that, we can create the or derive the Verilog code from this. So again, you see, we use the module instantiation using the previously designed decoder 2 to 4, right? DEC1, let's say, for example, this is DEC1 and this is DEC2. Z1, Z1 is, what is Z1? Z1 is this signal actually, not W2, and EN. So this will be Z1, this will be Z1, and this will be Z0 using data flow modeling here. And here is the connection, Z1 W1 0 for this one, and Y0 to Y3, Y0 to Y3 for this one, right? And for the second one, Z0 here, this is W1 W0 here, and Y4 to Y7, and you can get this circuit. Another example of decoder is the 7-segment decoder, right? Used a lot in 7-segment application. So for this, you will have 4 input and 7 output, and this output is connected to this. For example, this A, B. So when we want to display number 3, for example, A should be equal to 1, B should be equal to 1, G should be equal to 1, C should be equal to 1, D equal to 1. So that will be number 3. F and E should be equal to 0, and so on. So it should be based on this truth table. For example, 0, number 0, so A should be 1, B 1, C, D, E, F, only G is 0. So that will display number 0. So this is the 7-segment decoder, right? So if number 0 come, it will display number 0 at the 7th segment. If number 1 come, right, in hexadecimal here, it will display number 1 and so on until we have number 9 here. 1001 is 9. And to write the code is quite straightforward. Yeah, we use case statement because we have the truth table already. So we can have case statement. So case W. Yeah, if W equal to 0, 0, 0, 0 or 0 in this case, the output should be this. If 1, the output should be this, and until the last one. And here we need to have a default here. Why? Because the input here is 4-bit. Yeah. So remember, if you have 4-bit input, you should actually have up to 15 combination. Now you have only 9 combination. So the rest you need to specify also. In this case, you specify the output other than this as don't care. All right. So if you don't have this, when you compile your Verilog code, you will get many warning. All right. Means that you will create the memory circuit for this if you don't specify this, right? So you can test actually using quarters prime, trying to write the code, this code, and without this default, and see what happened. Yeah. This is encoder, opposite of decoder. So it do the opposite work, where we have 2n input and we have an output. So this one is 4 to 2 encoder, and this is the code very easily. 1 if 1 W equal to 1, so we have B equal to 0, 0, and again because this is a case statement and you have 4 input, so you should have actually 15 combination. So other than this, yeah, you set to don't care as default keyword, right? And looks at the another type of encoder, we call it priority encoder. So the priority encoder is to encode based on the we call it priority. Yeah, for example, if the input is 1 here, we don't care already this one, whether this one is 0 or 1, and we should output this to the output y1, y0, and z. And if we have 1 here, we don't care already whether this is 0 or 1, and this should be the output. And if this is 1, we don't care here, and we have this. And this is the code, yeah, exactly based on this. So we have if W, we use case X, this is for priority case X, or case X means that we have the don't care in our combination. So if 0, 0, 0, 1, this one is no don't care. If this one is we have don't care, and y equal to 1 here, right? Until we have this, y equal to 3, 3 is this, 1, 1 is means that 3. But if other than this, we can use default again, and we have 2 statements in default. That's why we need to have begin and end. Y equal to 1, 1, and z should be equal to 0. Other than this, right? Y this one, sorry. So y equal to don't care, d is don't care, and z equal to 0, this case. That will be the priority encoder. So now we have learned multiplexer, we have learned decoder, and we have learned the encoder, and all of these circuits are very important in digital hardware. We will use a lot in the next design. Now come to the very important one, which is the adder, right? How we add the number in hardware. Okay, so before this, this is quite interesting because we can design, or we can create the hardware that can add number, right? The hardware is the is non-living thing, right? but we can create, or we can put some intelligence in the hardware so that it can compute, all right, can calculate. So this is quite interesting, yeah. Uh, uh, to have the hardware that can calculate. So how we create the hardware that can calculate? So the first one is the adder circuit. This adder circuit can add a number, but the idea is come from the manual calculation or uh, handwritten calculation, right? Or calculation by hand. Uh, so the concept is, yes, we learned this since our school day, where to add a number we can do that. We have x and y, x plus y. So we will have a sum, a product of the add, and we may sometimes has a what we call a carry. All right. So in binary there will be 4 possibilities to add number, and of course in binary, in digital, we have only two number, which is 0 and 1, right? So the first one is must be 0 plus 0, and 0 plus 0, the product will be 0 and the carry will be 0, right? Very easy. And if x equal to 0 and plus 1 at y, so the product will be 1 and the carry will be 0. And same one here, 1 plus 0, we have 1 and 0 carry. But if we have 1, x, y equal to 1, and we plus, the product will be 0 and we have 1 carry here. Interestingly, this one can be represented in the truth table, right? Using a truth table. So we can have a truth table like this, and we can have the circuit. If we have truth table, remember, truth table, we can generate the logic circuit very easily, where this is clearly, this is a C is the AND behavior, AND gate, right? Because you see 0 0 0, and if 1 1, we have 1. This is exactly the AND behavior. And if we have this 0 0, we have 0, and 0 1 or 1 0, we have 1 1, and 1 1, we have 0. This is exactly the XOR behavior, and we have XOR behavior of this. And yes, we have the circuit that can calculate now, which is called half adder. But the half adder is not good yet, because it only can add 1 bit number, and 1 bit number is very small, right? Only number 0 and number 1. So this is not very useful yet. So now we want to add more bit to have a very useful hardware that can calculate a big number, a number that we use every day, right? So for example, the number is 5 bit here, x is 5 bit, y is 5 bit. So again, in hand calculation, so this is x0, y0, we plus, the product is s0, and so on and so forth, and we can have the carry. And here is the example. If x is equal to 15 and y is equal to 10, and we add in binary, we have something like this, right? And when we observe here, all right, we can represent this position as something like this, where this is xi, this is xi plus 1, this is yi plus 1, this is si plus 1, and so on. And this is ci plus 1, right? This is c0. We can see that the c will be here, and we add to here, and we had the result, and c will go to here, right? So for that, we can create a truth table for this part, right? So for example, we have c equal to 0, 0 0 0 0 0 0. We can have c plus 1 equal to 0, and s0 equal to 0, Si here equal to 0, and this is for this. And for this one also the same, right? Also the same. When 0 0 0, we have this. When 0 0 1, we have this. So we can create a series of uh, of process here, right? And for one process here, we can create the circuit actually based on the truth table, and then we can have the Kanu map, and we can generate the circuit for this, right? Where we can have Si for this one, and Ci plus 1 for this one, and we can connect like this, yeah, where Ci is this is C0, this is C1, which is this one, right? If this is C0, so we can connect the output, the C1 to the next one. This is X. If this is 0 0 0 0, so this should be 1 1 and 1, right? So we can have like this, x1 y1, x1 y1, and this is C1 C1, and we have S1, and we can connect to how many adder that we want. So this is a good thing where we can create a big adder using a cascade connection like this. So this is a example of a 4-bit adder where we use this concept, right, to create a bigger circuit. And in this case, if we want a bigger circuit, we can just connect a more adder in the cascade orientation like this, or connection like this. So this is good, and this demonstrates the hierarchical design and also the modularity design, right? So again, here we can design one module FA here using Verilog. Very easy. We can use the code, the Boolean equation. So x and y, or x and ci, or y and ci. So exactly based on this equation, we can create this module. And for that, we can have a 4-bit where we can import or instantiate this FA into a new design, FA4 here. This is FA for one module, and this is FA4 for the complete 4-bit adder. So where we have FA, the name for this one is, for example, we name it as ADD0, and we have X0 with this one, Y0 is this one, Y is connected to Y0, CI is CI here, C1 S0, and the add number 2, add 1 here, X1 Y1 X1 Y1, C1 C2 S2, and so on. So we get the 4-bit adder here, and this 4-bit adder can be used to add a 4-bit number, right? So that is adder, how we add numbers in digital hardware. Now the interesting is that how to subtract a number. Subtract is quite tricky if we want to design a circuit or create the truth table like the full adder like this. But the good thing is that we can actually uh, manipulate the adder, right? For example, if we want to do the subtraction, So for example, if we want to do 4 minus 2, right? Actually, we can use adder to do this, because 4 minus 2 is actually equal to 4 plus minus 2. So here means that we can use adder hardware in order to do subtraction. The only problem is how to represent a negative number in uh, in digital, right? So to do that, we need to look at the possibility that we can have. So that's why we have what we call the sign number in digital. All right. So first, engineer or the scientist designed or invented uh, this concept, what we call the sign number. All right. So the first concept is called Sine and Magnitude, yeah, where the MSB is used to indicate the sign of the number. For example, if MSB equal to 0 means that the number is positive. If MSB equal to 1, the number is negative, right? And this is for unsigned number where all the number is uh, is magnitude. Yeah, so the unsigned number start from number 0 to the maximum size of the hardware. For example, if our hardware is 4-bit, so the number will start with 0 and end with 1111, which is 15 in decimal, right? But in signed number, right, here MSB will be the sign bit. Yeah? Here we call it sign bit, and the magnitude is this sign followed by the magnitude. So if 0 means that positive, if 1 means that negative. So this sign and magnitude representation, 0 and followed by 1, which is actually number 5, right? This is positive 5, and negative 5 is easily represented like this. Sign is 1 and 101 is the magnitude, which is actually number 5, so this means minus 5. But this although this representation is easy to understand, but it is not very useful and not easily used in hardware, right? And we actually don't use this representation in digital hardware. So what we will use is what we call the complement representation, right? So the complement representation, we have two type of complement. The first one is called first complement representation. For example, we have negative 5. If your number is 4-bit, yeah, so the maximum is 1111 minus 0101, so you have 1010. So this is first complement of 5, or number minus 5. Or easily we can actually using the complement concept, where 5 in binary is 0101, and we just complement, we get 1010. This is minus 5 in first complement, right? So in theory, minus 5 is generated, for the first complement for minus 5 is generated this way. Yeah, so this using this formula, where k, the number that we want, is equal to 2 power of n. All right, 2 power of n in this case is, if our system is 4-bit, n is equal to 4, so 2 power of 4 is 16, minus 1, which is 15, minus the p, the complement value, the value that we want to complement, right? So in this case, for example, number 5, so 2 power of 4 is 16, minus 1 is 15, so this is 15, minus p is 5, so we have 1010. So this is the first complement. But the easiest way is to just complement every bit of number 5, then you can easily get this. That is first complement. What about second complement? Second complement is a modification of first complement where, so for example, using the same value to how to get second complement for number 5 or minus 5, it is 2 power of n 16, right? This is 16 in binary, and we minus number 5, this is 5, and we have 1 0 1 1, and this is actually second complement representation of minus 5. And if minus 3, this is minus 3. Or we just in using hand calculation, where what we do is, again, number 5 is 0 1 0 1, and we try to complement every bit. So we have 1 0 1 0, and we plus 1, and we get the second complement of 5 or minus 5 representation in second complement. So we have 1 1 0 1, right? So this is minus 5 in second complement representation, right? 1 0 1 1 1 0 1 1, very easy. But why is this important? The question is, why is this important? So before that, look at this. So this is a 4-bit system, sine and magnitude. We can see that positive 7 is the same, positive 6 is the same, 0 is the same, but negative side, yeah, 1 0 0 in sine and magnitude represent minus 0, actually 0. First complement is minus 7. This is mean minus 7. Second complement means minus 8. 1 0 0 1 in sine magnitude is minus 1. In first complement is minus 6. In second complement is minus 7, right? So we will see which one is good for implementing the arithmetic or subtraction in computer. Yeah, which one is good to be used. So this one is not useful, all right? But look at this and this. This one is, first complement is quite good because we can do something like this. For example, we want to add a number, positive number, 5 plus 2, this is 5, this is 2, we add, we have 7, this is 7, right? Very easy. And this is the good thing is that when we have negative number here, minus 5 plus 2, of course we can use the adder, this is adder, right? So this is minus 5, first complement, and this is 2. When we add, we have 1 1 0 0. 1 1 0 0 is, when we look at this in first complement, is 1 1 0 0 is minus 3, right? Minus 3. So this is minus 3. The answer is correct. Minus 3. Minus 5 plus 2, minus 3. Yes, this is good. So this calculation cannot be done using this representation. That's why I said this one is useless. Useless. This representation is useless. But this first complement addition or first complement system is very promising because we can have something like this. This is correct. This is correct. What if we do this? 5 minus 2. This means that we want to do subtract, right? Subtract. 5 minus 2. Or we do 5 plus minus 2. So again, we use adder, the circuit that we have already. Adder. So 5 minus 2 or 5 plus minus 2. This is 5 plus, this is minus 2 in first complement representation. And when we add these two, we have this. And we know that 5 minus 2 is, the answer is 3, and this is 2, right? So the answer is wrong here. So what we need to do is we need to do correction where we take this carry to put here, and we add with the carry, we have 3, and this is the answer. So 5 minus 2, we have 3, which is good also. But we have to do two addition, right? Adding 2 times. This one use one adder, and we have another adder here. Same as this one, minus 2 minus 5 minus 2, or minus 5 plus minus 2. We should have minus 7, and this is minus 5. This is minus 2. And when we add these two, we have 0, 1, 1, 1, which is not the minus 7 yet, because 1, 1, 1 is what is that? 1, 1, 1 is minus 0. Right? This is not correct. So what we do is that we need to have 1 at here, and we have 1, 0, 0, 0, and 1, 0, 0, 0 is, yes, 1, 0, 0 is minus 7, correct? Minus 7. So it looks like we can use first complement number to do subtraction, right? Subtract 5 minus 2 minus 5 minus 2, right? But the problem is that when it's come to this combination, all right, we need to add another one. Means that the hardware is looks complicated, right? We need to have 2 addition here, but this one no need, this one no need, but this one we need. Maybe we need to have another option. So let's look at the second complement addition. So for second complement addition, this one is easy, 5 plus 2. So just using the adder, 5 plus 2, we have 7, no issue. This is minus 5 minus 2 plus positive 2, minus 5 plus positive 2. Yes, again we use adder, and we have minus 3. Is it minus 3? Minus 3, where is it? Minus 3, 1, 1, 0, 1. Yes, 1, 1, 0, 1 is minus 3. No issue. Straight away we get 5 minus 2. So 5 minus 2 is positive 3. And let's look at this. This is 5. This is minus 2 in second complement representation. And we have the output is like this. And because our system is 4-bit, this is bit number 5, we can ignore actually. All right, and the answer is 0, 0, 1, 1. So this is 3. 0, 0, 1, 1 is 3, correct. So no need addition, extra addition like this. Then we get the answer already. What about this? Minus 5, minus 2. We have minus 7. So this is minus 5, this is minus 2. We add, we have this. And this one also, because this is bit number 5, our system is 4-bit. So this we can ignore actually. So the answer is 1001. Is it number minus 7? 1001 minus 7, exactly. So means that when we use second complement, the subtraction become possible and easy by using second complement addition. All right, we use adder also, but we changed the number, or we used second complement to represent a negative number, right? So that is why we use second complement in computer. So if you use computer, you open your computer, when you do add subtraction, actually it is using second complement addition. All right, and your computer, your handphone, your calculator represent a negative number in second complement format. Yeah. Okay, this is a second complement subtraction. Subtraction is actually the same as that one. Yeah. plus 5 plus 2 minus plus 2, we change to this. All right, and we can get this. So actually what we do is same thing, where this one is plus 5 minus plus 2. So you will have plus 5 minus plus 2. So this is actually plus 5 plus minus 2. So you still use an adder, right? So this is actually the same thing, right? So this is the same thing as the previous one. Okay, this is the same. So plus 5 minus minus 2, this is actually plus 5 plus 2. That's why you have 5 plus 2, you have this. This is minus 5 minus 2, this is actually minus 5 plus 2, minus 5 plus 2, you have this, right? So that is actually how we implement the subtraction in digital hardware. So this is adder subtractor circuit, where we combine, because actually just like we learned just now here, actually subtraction here, we want to do subtract. Actually we use adder, all right, only that we change the number here into or we represent the negative number by using second complement representation. So everything is using adder actually, right? So this is the hardware or the circuit for the adder subtractor circuit. All right, and this circuit can perform either add or sub depending on this control signal. We have input X here, right? N bit, yeah. So can be 4 bit, can be 8 bit, can be 10 bit, can be any bits. All right. So this is another one input of the adder. This is another input of the adder, but this input Y is connected to this XOR gate before it enter the adder here. And this is the C in, or in this case we call C0, right? C in for this adder, and this is the output. So we have S0, S1 until Sn equal minus 1, and this is C out, the carry bit. And how this circuit work is actually like this. If we take 1 bit adder subtractor circuit here, where we have the X and we have another XOR, okay, this is a 1 bit adder. So if, for example, we want uh, to add a number, or we want this circuit to be an adder, so what we do is that we set this signal this signal to 0, right? So if this one is 0, and this is XOR gate, right? So let's name this XOR gate. The output here is F, and the input here is add sub, quite long here, change to A. Okay, so let's look at the behavior. We have A, Y, F. We have 0, 0, 0, 1, 1, 0, 1, 1. And if 0, 0, we have 0, 1, 1, 0, 1, 1, 0. Let's change this to YA better. Okay. Oh no, sorry. AY is the best. AY. So look at this. If A equal to 0, if we set this signal to 0, right? 0. So what happened is that F will exactly equal to Y. You see? F is exactly equal to Y. 0, 0, 1, 1 means that Y here we have Y. And if this is 0, C in equal to 0, right? C in equal to 0 means that the output here is equal to S equal to A, or not A, X plus Y, because this is adder. This is adder, the adder circuit. So the output here, this is 0 and this is Y. So the output here will be S equal to A plus Y, right? But if we set A here, or this signal equal to 1, this equal to 1, and of course this equal to 1, 1, and 1. So what happened is that if A equal to 1, you see the output here, if A equal to 1, the F is complement of Y. If Y equal to 0, F equal to 1. If Y equal to 1, F equal to 0. This is complement of Y. So we have Y bar here actually. If A equal to 1, we have Y bar. Means that this output is the first complement of Y. Yeah, or what you call this is first complement of Y. And when we have this is first complement of Y, if we have this adder, so X plus first complement of Y, and remember this is another one. So we have S equal to X plus Y complement plus 1. So Y complement plus 1 is actually second complement of Y, right? This is actually X plus second complement of Y. And remember, X plus second complement of Y is actually X minus Y. So that is how this circuit works, right? When we set this signal to 0, this circuit will act as an adder. When we set this signal to 0, this circuit will act as an subtractor. So that is how the circuit works. All right. So I think this will our lecture today will end here. We will continue the arithmetic overflow next week. But before we stop, you can uh, get further information, addition information, and also how to design this using Verilog code in my previous tutorial. I will share with you in Telegram group so that you can go to or learn from that YouTube video. Yeah, right. So this is the channel. I have the this designing adder subtractor circuit in Verilog. So you can refer to this. Here you can learn
about the license, and because we use the
design in
FA2,
and try to simulate the circuit.
yeah, so how to do that?
Right. So based on this tutorial and what you have learned today, I will give you the first assignment by this week. So remember, in the assessment, in the test, in the final exam, it will be an open book assessment. So the question is open-ended, and if open-ended means that the answer can be any answer. You can have many solution, many correct solution. Your solution with your friend can be different and should be different, and both can correct. Yeah. So it will be depend on how you design the thing, how you understand the thing, and of course you will need to use the software in order to write your code, simulate, and get the answer. So you will need to use the software a lot. So please, yeah, go to the tutorial and try to learn from the tutorial. And this course, because it involves the programming, and remember, programming, to learn programming, the best way is to have your computer, all right, type the program and run the program and see what is the output. And if you have the error, that is a good thing actually, because you will learn what is the error, and you will try to debug, try to find the problem and try to correct it. So you will learn from experience, right? So I think uh, we should stop here. Almost 5 o'clock already. Okay. So any question before we stop?